In this video, I'm going to be talking about simplest radical form and a couple of different ways to actually reduce these radicals. So I'm just going to use one simple example, and that is the square root of 48. So I want to reduce this so that the number underneath of the radical, that's called the radicand, is as small as it possibly can be, and I've taken the square root of different factors, as many as I possibly can. So there's one train of thought, and that is, the first one, is find the biggest factor that is a perfect square. So I do think that this involves a couple less steps than the other trains of thought. So your perfect square examples are 1, or 0, 1, 4. These are the ones we want to start with. 9, and then 16, 25, 36, 49, so on and so forth. So that's 2 squared, 3 squared, 4 squared. You get the picture. So I want something that I can actually take the square root of. So 4 does go into 48, but I want to look at these 4. They're all less than 48 and see if there any more of them are factors. 9's not a factor, but 16 is. 25 and 36 aren't. So 16. So the square root of 48 can be written as the square root of 16 times 3. And then I can break those square roots apart. It's still 16 times 3. They're just in their own little separate houses now. And I can take the square root of 16. That equals 4 radical 3. And that's as simplified as it can get. The second train of thought is to go ahead and break the root into its prime factorization. So what that means is that I do have 48, and I'm just dividing it into its little factor tree. So that's 2 and 24, that's 2 and 12, that's 2 and 6, and that finally is 2 and 3. So when I have the square root of 48, I actually have the square root of 2 times 2 times 2 times 2 times 3. Okay, so I can actually pair these off. So I can pair those 2's off. So that becomes the square root of 2 squared times the square root of 2 squared times the square root of 3. That 3 is a little bit of a loner, but it will be all right. So what happens with these symbols, the square root and the squared are opposite functions. So they cancel each other out. So that's the square root of 2 squared, which is 4. Square root of 4 is 2. And it's the same as this one, times the square root of 3. So that is still 4 square root of 3. The third method of thinking here is that you can just factor and continue. Factor and continue. This is what I think actually takes the longest. So the square root of 48, we could have done originally 2 and 24. Or we could have started out with 3, square root of 3 and square root of 16, shortest method. The square root of 4 and the square root of 12, the square root of 6 and the square root of 8. With any of these other 3 options, 1, 2, 3, I would have had to continue breaking it apart. So that's the square root of 2 and the square root of 2 and the square root of 12. And that one I can actually take the square root of, so that's cool. That's 2. And then 12 breaks into the square root of 4 times the square root of 3. So that's going to get me there a little bit faster. 2 times 2 times 3. That's 4 radical 3. So some options are a little bit longer work, and others are a little bit faster. So if you can go ahead and recognize the biggest factor that is a perfect square, that's probably going to cut down on some work. If you break it down to prime factorization, that's my second option. And then just fiddling with some of the other factors is the third method of thought that I would approach. But I would definitely try to use the first two options first. All right, good luck.